welcome to this lesson on redshift. We're going to talk about redshift and we'll talk about how it relates to the Big Bang Theory today. So, it is SP7 if you're following along using the Edexcel specification. And we're going to cover 3 different points. We're going to be able to describe how the movement of a wave source affects the observed frequency and wavelength, describe the amount of redshift observed in galaxies at different distances from Earth, and explain why the redshift of galaxies provides evidence that the universe is still expanding. Now, before we can start, let's recap some basic physics from earlier on in your physics career. When we have sound waves, we have to remember that sound waves are produced as pressure waves. So they are longitudinal waves, and we kind of represent them sort of like that, where the distance between 2 peaks would be the wavelength, and the number of peaks in a given time would be the frequency. Now, the frequency of the wave is really important here because that is determined by how fast the wave is moving, but also the wavelength between them. So if we have a high frequency wave, and we'll draw that as a frequency, as a displacement time graph, as a pressure time graph, then we would have lots of waves in a given amount of time. And if we have a low frequency wave, then we would have very few waves in a given amount of time. So there'd be much more space between them. And a high frequency wave is a high pitched wave, and a low frequency wave is a low pitch wave. So we can define the sound by the frequency and with it the wavelength. So as we can see on the slides above, high frequency, high pitch, low frequency, low pitch. So let's look at something called the Doppler effect. Now, you'll all have experienced this in your everyday life, and the Doppler effect is going to explain what we're going to see on this video. Okay, so there was a car moving at quite high speed, and you could hear the horn before, you could hear the horn as it passed, and you could hear the horn as it was passing you, and you could hear the horn as it was moving away. So 3 different points that we're going to consider the sound we heard. So we'll draw 3 cars to show the 3 different positions relative to the observer. And here is the observer. So this is the person in the middle who's watching the cars or the car go past. So in the centre, we know that the frequency would be the same as if the person was stood with the car. So let's say that frequency was 20 hertz. So 20 hertz you would was 25 hertz. And as the car went past, the frequency of the horn was in fact a little bit lower. So we've got 15 hertz. Now, why is that happening? Well, that is because of something called the Doppler effect, which literally states that it is the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. Well, let's look at that in more depth, and we're going to use my little friend here, a rubber duck. So here's the rubber duck between two scientists. We've got the scientist who's wearing a grey t-shirt and we've got the scientist who's wearing a red t-shirt. And this duck is going to quack. Now if the duck is stationary, then the sound waves from that quack are going to move at exactly the same rate to the left, to the right, to the top and to the bottom. So the duck makes a quack sounding like that. The person in the grey is going to hear that, and the person in the red is going to hear that. It's exactly the same. The sound has not changed because the sound waves are reaching you at the same time, at the same speed. Okay, but what about if the duck is moving? Well, if the duck is moving towards the person in the grey, then we see we're going to bunch up those sound waves at the front because he is catching up with the wave he's emitted, making the distance between the waves smaller, which actually means the frequency's gone up, and he's going to move away from the wave he's emitted from the waves towards the red side, towards the person with the red jumper. So here we can see the duck is still going to make the same quack, but the person in front of the duck that he's moving towards is now going to hear, and the person behind the duck that the duck is going to move away from is going to hear, because the frequency has changed due to the fact that that duck is moving. I want to go through that once again because I think this is really important and quite a complex idea to understand. So the duck, when it's stationary, all the sound waves move apart at the same rate, they have the same speed, the duck is not moving, so therefore the sound waves travel the same distance in the same time. So all of the waves are concentric to each other, it means the distance between those waves are equal. Now when the duck is moving, the duck is going to emit the wave but actually catch up towards it as it's moving towards the wave and move away from the wave that it's emitted behind it. So again, listening to those differences, the duck, the person in grey and the person in red. Higher frequency for the person in grey, lower frequency for the person in red. So we better have some notes here because this is quite an important idea. So we'll go with a duck. Why not? So there's my duck. Okay, so the duck, when it's emitting his waves, sound waves, when it quacks, they're all going to be concentric. But as that duck starts to move towards the waves at the front are going to be squashed, and the waves at the back are going to be stretched. Hence we could hear the car have that apparent change in its frequency as it passed us. So waves at the front are squashed, waves at the back are stretched. So here the wavelength is going to decrease and here the wavelength is going to increase. Now if the wavelength decreases, well in fact the frequency is going to increase and here the frequency is going to decrease. So we can see that as that duck starts to move, he's going to catch up with his sounds, so there's going to be a different, with his sound waves, there's going to be a different sound for the person in front, the observer who he's moving towards, compared to the observer he is moving away from. And obviously if you sat on top of the duck, so if you were riding the duck here, then you would hear the same quack because you'd be moving at the same rate as the sound waves themselves. Now, that explains it in terms of sirens, it explains it in terms of cars passing us. But what it also can explain is the idea of how light changes. Now, in the same way that the sound waves are being caught up and moved away from, light waves can be caught up and moved away from. You have to be travelling faster to make this a bigger difference. But any galaxy that is emitting light, because it has stars, so here are some stars, will also emit light in those concentric circles around them. So if the galaxy wasn't moving, all the light would be emitted in a normal way. But because galaxies are moving, and we'll come to that a little bit later on in this lesson, those light waves that are emitted in front of it are closer than the light waves that are emitted behind it. So the apparent wavelength is going to decrease, which means the frequency is going to increase as it's moving towards us. Obviously we're here on Earth stood looking at it, but if you were stood behind it looking at it, then we would see that the wavelength is increasing, so the frequency must decrease. Well, what does that mean when we actually look at these colours? Well, if we go back to the electromagnetic spectrum, we can remember that Richard of York gave battle in vain, or run over your granny because it's violent. We've got the order of the visible part of the electromagnetic spectrum, and we'll deal with the visible part for the moment. Now let's imagine I have got a single light source that's emitting one colour, that's yellow. Now as I'm moving towards the Earth, which we can see over here, we've got the nice Earth, some countries, some land, then the frequency is going to increase, but the wavelength is going to decrease. So the wavelength is going to get longer. Now, if we remember from our electromagnetic spectrum lesson, a longer wavelength is towards the red. So the wavelength is going to get smaller. Now, if the wavelength is going to get smaller, and I was detecting these electromagnetic waves that have been emitted from our galaxy, then we will see that this red line has no longer remained where it was, so this black line where it was in the yellow. It is going to have moved towards the shorter end of the spectrum, and it is going to have been blue shifted. So we are blue shifting the line towards the blue side. So the line is being shifted towards the blue side. Now let's imagine there was more than one line, so maybe there were two, so two different colours being emitted, then we would see the same blue shift with the second line. So it's all about the emission of that part of the spectrum having been shifted towards the blue side if the galaxy is moving towards us, because that wavelength is shrunk. Now, what about if we're the observer on the second planet? We'll be observer B. Well, observer B is going to see the wavelengths increase. Now, if the wavelengths are increasing, then we are going to see a shift in the opposite direction of the spectrum. So what was in the yellow and orange, so two colours here, has now shifted towards the red. And in fact, it might shift so far that we might even be into infrared. So we might get our two shifts over there. And we call this a red shift. So the red shift happens when an object is moving at high speed away from the observer, emitting light or emitting electromagnetic spectrum. It is being shifted into the red side of the spectrum. The blue shift happens when an object is moving towards the observer at high speed and emitting electromagnetic waves. Then those waves are going to be compressed and are going to be squashed together and become part of the blue part of the spectrum, or shifted to the blue part. So redshift, those waves have been expanded because they've been stretched as the galaxy is moving away from what it's emitted, so we end up in the red side. And blue shift, they're being compressed because we're moving and we're catching up with those waves as we're moving, and that's causing the blue shift. Now this can all be explained by describing what's going on in terms of the energy levels that the electrons are in. Now, energy levels really comes back into it at A level, but we have covered this earlier on in our radiation topic. We can see here we've got a laboratory source of light which is emitting specific wavelengths of light. So we can see that the absorption of that light source is leaving us those black lines, what we call the absorption spectra, in the continuum, so all of the different colours of the visible part of the electromagnetic spectrum. Now, when a galaxy is moving away from us and emitting those same absorption spectra, then we can see that there has been, in this case, a shift to the red end of the spectrum, causing a red shift. So we would know that this is a galaxy that's moving away from us. So it's all about being able to use these spectral fingerprints to describe how the galaxy is moving away. And the faster the galaxy is moving away, the bigger the red shift, or the faster it's moving towards us, the bigger the blue shift. So we can learn quite a lot by looking at these spectral fingerprints. Now, this was a fact that in 1929 a man called Edwin Hubble discovered. And actually it wasn't Hubble on his own, there were some other scientists involved as well. Hubble used the Harvard computers, and one notable person in the Harvard computers, and these were women who looked at the pictures that he was taking of the night sky, and one of the ladies we should consider being quite instrumental in this is Henrietta Swan Leavitt. Now, in 1929, Edwin Hubble discovered two facts. He discovered that the light from distant galaxies was redshifted. So he looked at all these different galaxies. He was able to compare those emission spectra and look at the comparison to the lab. And he also realised that the bigger or the further a galaxy is from us, the bigger the redshift they have. Now, I'd love for you to pause the YouTube video here and draw a sketch graph. We're going to have distance along the x-axis versus redshift, which is along the y-axis. So well done for having a go at that. Hopefully you managed to draw something that looks a little bit like this, where we've got a nice straight line going through the origin. The greater the distance, the greater the red shift. And what this has led to is to this idea that the galaxies that are further away from the Earth seem to have a greater red shift. And if they have a greater red shift, that means they have a greater velocity. So here is Hubble's actual diagram, so you can see it. We've got the distance along the x-axis, and as we have now linked redshift to velocity, we've got the velocity difference along the y-axis, and we've got a nice set of data that's pretty much a straight line through the origin, which is 0, 0 here, but also a straight line as we increase. Well, it led Hubble to two really important conclusions. He has concluded to say that the distant galaxies are moving away from us. All of them, pretty much every single galaxy he looked at was moving away from us. And he also realised that the greater the galaxy is, the greater the speed that it's moving away. And it led him to a really important question. Why should those distant galaxies be moving away from us? We're nothing special. We're not a special place in this universe. If we were to turn time backwards, so at the moment we're saying that the further away a galaxy is, the faster it's going, because the bigger the red shift. And if we look at the ones that are closer, they're all moving away from us. It's got a smaller velocity, and here's the Earth. And we've got one over here that's going away at a great speed, and a much closer one that's going away at a much smaller speed. But if we reverse time and bring them backwards, it actually tells us that all those galaxies must have been in one place at one time. And realistically, if we're thinking about it as maybe Hubble would have done at the time, they might have all come back to that one spot, and that one spot appears to be us. But we're not anything special. Why should those distant galaxies be moving away from us? Well, we're going to explore that in more depth in the next lesson, where we're going to have a look at the Big Bang Theory, and we're going to consider what's going on with that, and we're going to consider what the evidence is to go with it. So, thank you very much for watching this video. Watch out for the next one in the next week, and if you've got any questions, you know how to contact me.